Hi, and welcome to Parametric Camp. My name is Jose Luis, and in this video, I'm going to write a bunch of examples where we're going to do very simple ASCII art, such as, for example, drawing rectangles, solid rectangles, border width rectangles, circles, pyramid, like simple geometry. But I would like to use this video to illustrate the concept of nested for loops. Because this video, if you're here, you might be coming from this video is part of a larger playlist called Learning C#, Introduction to Programming for Designers. So at this point in the playlist, we just learned a bunch of really interesting techniques, such as, for example, conditional with if statements, and we just learned for loops and nested for loops. And actually, the previous video to this one was using for loops to write numerical sequences. So in this one, I want to use ASCII art as a vehicle to practicing nested for loops, which are also like a very important technique. So what I'm going to do is I'm going to implement a series of different geometrical objects using nested for loops, and we're going to do it in an ASCII hacker way. So it's going to be cool. Grab a coffee because it's going to be a little intense if you're new to computer programming, but it's going to be super cool. And the first one that I'm going to do is going to be a very simple rectangle. I'm just going to use a character, so for example the pound sign or any other character, and I'm going to use that to replicate it in a nested for loop so that we have a full solid rectangle with as many widths and with whatever width and whatever height we want to use. Okay? So let's do that. So the first thing I'm going to do is, because I want repetition, I want to use a for loop to, for example, create a line of characters. All right. So what I'm going to do is I'm going to create a for loop where I'm going to say, I'm going to create a variable type called I, and I is going to be less than, for example, let's say that the rectangle is going to be 50 characters in width. So what I want to do is I want to say I is going to be less than 50 units, and it's going to increment in units of 1. And then each one of these iterations, I'm going to write to the console a character. So for example, the pound sign. And after we have finished doing that, I'm going to write to the console an empty line character so that we can move on to the next line. If I do that, then what we can see is that in my console that shows up on the wrong screen, we're going to get this row of characters one after the other, and then you can see how the cursor is on the next line. So the cursor is ready to keep drawing more of these. Okay? So now, if what I want to do is to draw a rectangle, which is a lot of these lines together, I have been able to use repetition to draw a lot of characters in one line. So what I would want to do is I would want to use repetition to repeat the operation of drawing all these characters in one line. So the idea is that now that I have a for loop to draw all these characters, I can wrap that inside of another for loop that is going to make the drawing line operation repeat over and over again. So very simple. So I can go back to the parent, and then I can wrap that those lines of code inside of another for loop. For this one, I'm going to use the variable name j. It's very common when you nest for loops to start with I, then go to j, and if you're nesting a third one, do k, etc., etc. So j is going to be less than, for example, 20 rows, and j is going to be equal to plus plus. And then I'm going to take all this code, and I'm going to wrap it inside of the for loop. And I'm taking all the code because if I did not include the right line, see what will happen. So all the lines will be drawing one after the other because I'm not moving my cursor to the next line. So that's why what I need to do is I need to move this after the for loop so that every time I draw a line, then I go to the new line, and then, oops, I click on the wrong thing. And then I have my rectangle with my 20 lines of characters. All right? How is this going? Is this cool? Now, obviously, if you know me already, you know that I don't really like hard-coded numbers very much. So these two numbers, 50 and 20, represent the width and the height of the rectangle. So why not turn those into variables, right? So for example, and we're going to say int equals int width is going to be equal to 50, and int height is going to be equal to 20. All right? And then here I'm going to replace this variable with width. I'm going to replace this with height so that I can have a bit more of fine control of the size of this rectangle. And now if I wanted to make it a little smaller, so for example 40 and I don't know, 12, then I can just change those two variables and I can adapt the size of my rectangle. All right, and you probably know where I'm going with this. By the end of this video, I will ask from the user, I will ask input, I will ask for values, and then we will draw all these geometrical sequences based on whichever size the user has inputted. But we're going to do that, we will do that by the end of this video, okay? Right, so I have been able to draw a simple rectangle, and I'm actually going to write a message here where I'm going to say solid rectangle, and I'm also going to write another empty line character here to leave myself some room for the next operation, the next ASCII figure that I'm going to draw right now. Wonderful. So let's go to the next one. The next one we're going to do is going to be a rectangle that, but instead of being solid, it's going to have a border. So border rectangle, or a non-filled rectangle. Okay. So how is that going to work? Well, I'm going to, first of all, I'm going to use the same width and height. So just for symmetry. So pretty much what I want to do is I'm going to copy paste all the code, and I'm going to run this, and you can see I get the same result. But now what I need to do is I need to be able to figure out first a variable that is going to define how many of these characters are part of the border, 1, 2, 3. And then I need to figure out for each one of these characters here, so for this one here, for this one here, for this one here, etc., I need to figure out if they are part of the border or if they're not. So that's actually going to be very simple with a numerical check. So let me define a variable called border width, and that's going to be equal, for example, to 3 characters, right? And then what I can do is, first of all, let me think through what is going on here. You can see that as I am moving, so this whole row in the for loop has a j value of 0. This whole row has a j value of 1. The third row has a j value of 2. So for this line here, we can see that if we check if j is less or equal than the border, then we're going to know that all these characters should be either a pound or a different sign. So I can write here, I can say if the value of j is less or equal than than border width, then what I want you to do is I want you to print a pound sign. Otherwise, if it's not, I want you to print some other sign. It could be just like a white space, but I'm going to use the dot so that we can actually see which ones are empty and which ones are not. If I run this code, you can see that, it's starting to work. So we get the first line, but I messed up. I set the value of 3, but it's actually 4 lines because I introduced the less and equal. So I'm going to remove that, and I'm going to execute again. And I'm going to, okay, so that's going to be great. So that's working. The first line above is working. How could I do this other line here? What is the rule? Well, the rule is also very simple. J, we know that for each one of the rows, j is 0, 1, 2, 3, 4, blah, 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 whatever, all the way until the last row, in which the value of j is height minus 1, because we always have like one extra value, right? So if what I do is, if I check whether if j is less than the border or if I check that height minus the border is also greater than j, then if any of those two conditions meet, then these symbols here should also be the pound sign. So what I can do is if j is less than the border width, or if j is greater than height minus the border width, then the symbol should be a pound sign. Otherwise, it should be a dot. And let me run this. And I think, oh, sorry, total mess. I forgot, I messed up. This is the and symbol. And what I meant to do is like if it's one thing or the other. So that's why I'm using the double pipes here. And if that's true, then you can see that this is almost working, but I'm getting 1 unit less. So it should be height minus 1 minus the border. Okay? So now we have the width of the rectangle here. So 3 for j, and 3 at the beginning, and 3 at the end. Now, similarly, we know that now we have to figure out the border on the left and on the right. So we also know that as we move to the right, what changes is the value of I. So I is 0 for the first column, 1 for the second column, 2 for the third column, etc., etc. So as we move to the right, the value of I increases. So we also can very easily tell that if I is less than the width that we're trying to get, then the dollar, the symbol should be the pound sign. Otherwise, it should be empty. So another one that we can check here is, or if I is less than border width, then at that point, we should also print the pound sign. So let's see if that works. Ooh, it's working. So we got the pound sign here now. And what about this one? Well, same rule as before. If I is less than the border, or if I is greater than the width of the rectangle minus the width of the border, then we should also be printing a pound sign. So I'm going to do here, or I is greater than width minus 1 minus the border width. And I'm actually, just for the sake of visual flavor, I'm going to input this. It just makes things a little easier to read. And then, now I have a rectangle, and the rectangle has 3 characters bordered all around it. So now I can nicely change this to a white space character, and then I can start playing with this. So for example, one character width, so that's the border rectangle. Or if I want 5, for example, now it's going to be like a thick rectangle. And you can see that it's not proportional, but that's not proportional just because characters are higher than wider. So, but that's part of how the system works. So we can't really change that. So I'm going to leave this at a nice value of 2 and execute this, and we can see that now we have a border rectangle. All right, cool. So let's go and try the next one. The next ASCII art that we're going to be doing is going to be a checker pattern. All right. So a checker pattern is going to be basically drawing a rectangle, and then each one of the characters, alternatively, we're going to turn them on or off. So how am I going to do that? I'm going to start off also from the similar code, from the full rectangle. I'm going to stop here and say this is going to be a checker pattern, right? And then here you can see that I am basically just drawing everything full, okay? So what I need to do is, for this checker pattern, I need to find a way to detect that I want the first element to be on, the second element to be off, the third element to be on, the fourth element to be off, etc., etc. And I'm going to do that by also taking a look again at the values of I and j, because I and j are basically telling me the location of each one of those characters in my 2-dimensional grid. If you think of this, if this was a screen, like a computer screen or a cell phone screen, we could think of each one of these characters as a pixel. And we can think of I and j being the location of that pixel on the screen. So I grows in this direction, starts at 0 and ends at 49 in this case because we have 50 elements, and j grows in this direction. It starts at 0 here and goes down in this way. So actually, from now on this video, I'm going to start referring to each one of these characters as pixels. They're not exactly true, but I want to make that analogy because it will make our life easier to when we move on into thinking about computer graphics. And also, this is also one of the reasons why in most computer graphic environments, the coordinate system is not on the bottom left, it's actually on the top left corner, and x grows in this direction, and positive y grows in the bottom direction, as opposite to mathematical notation. Okay, so we're going to start thinking of I and j as the location of where my pixel is on the grid. And what I want to do is, first of all, let's start working in this direction. If we know that the location I of the pixel is, for example, odd or even, then we know that that pixel should be on. And if we know that it's even, then we know that it should be off. So for 0, for 2, for 4, I'm going to want to turn that pixel on. So how can I do that? Very simple. I can say if I modulo 2 equals 0, then the character that I want to print is going to be the pound sign. Otherwise, if it's not, then what I want to write is going to be the character, for example, a dot, so that I can see now a bit more clearly what's on and what's off. If I do that, you can see that now what I get is this like vertical stripes. So basically I am getting columns of on and columns are off. Let me just replace this with a white space, and it's going to make things a bit clearer. We're getting vertical columns that are on, vertical columns off, because at this point we're only looking at the value of I. All right, and that's why every row, no matter how high where it is in the columns, every row is getting an on and off pattern in the same direction. Now what we need to do is we need to say, well, I also want to take a look at j. And if j is odd, is 0, then you leave things like they are. But if it's 1 or 3 or 4 or 7, then you change the pattern and then you move everything to the right. You're not really moving. So what we're going to do is we need to find a numerical rule between I and j so that things move to the right. So for example, one pattern that we could use is, we know that this line here has a j of 0, right? And I, 0, 2, 4, etc., etc. But we know that the second row has a j of 1. So something that we can do is, if to every value of I here, we add the number 1, then basically the first value here, which has the first pixel that has a I0, now is going to get an I1, and therefore it's going to be odd and it's going to be off. The second one, which had an I of 0, of 1, is going to become 2 now, and then it's going to be turned on. So if we add the value of 1 here, then we're actually kind of moving everything to the right, right? Now in J2, we don't want to move anything. We want the things to be as they are. But if you think about this, if we add here the value of 2, anything that was even, what is still going to be even. Now, but if we go to the value to here, to j equals 3, if we add to all these values, if we add an even value, then we're going to change. Whatever was odd is going to become even, and whatever was even is going to become odd. So the trick here is that if we add together the value of I and the value of j, the x location and the y location, anything that was even, if we add an even number, is going to stay even. If we add an odd number, it's going to become even. So if we, on even rows, things will stay the same, but on odd rows, then things are going to shift by 1 unit. So this is just as simple as saying, I want to calculate I plus j, and then from this result, see if the value is even. And if that's the case, then do the pound sign, otherwise do a white space. And if I run this code now, you can see that, ta-da, I get a checker pattern here. Woohoo! Yes, we got it. But this checker pattern doesn't look very sexy. There's something about the pound sign that is making it very difficult for me to understand, to see this as an actual full pixel, all right? Is there anything we could do to draw this more as a full pixel? There is actually. So if you think about the ASCII table or the characters that we have available for ourselves to draw things with, at the beginning of computation times, we had just very simple characters, numbers, letters, and some basic punctuation, parentheses, open and close, commas, dots, and some curly brackets, etc. But then when they extended the basic set of ASCII characters, they came up with a bunch of really funky characters. This was back in the times when there were no computer graphics. It was just like characters on a green screen, right? So in order to create some geometry, they came up with these fancy characters that are like simple pipes, double pipes that connect crosses in two directions, etc. Even these gradients, so pixels that are on and off with more density, and these characters here, which are like a full pixel, so the character space full with all solid pixels, or half a pixel, left pixel, half left right pixel, and half top left pixel. So if we find this character somehow and we print that, then we will have a full solid pixel. However, where can we find that? Well, we could find it with its ASCII number, but that is a little cumbersome to run. So on my system, on Windows, I have this thing called the character map. So you can just do search and type character map, and it's going to give you something that you can use to navigate on any typeface that you have. You can use to navigate all the characters that are available. And I have chosen Courier, and I've chosen Courier New because one is one of the font sets that has the most characters. And if I keep scrolling down, you can see that as I reach the end on my system, I reach these funky characters, the pipes with the angles that go up and down and have crosses and T's, etc. Single pipes, double pipes. So this is actually really, really good material to do ASCII art. And then there's this one, which is called the full block. If I double click here and I copy it, now it's on my clipboard, and then I can paste it here now and make it a full solid pixel. And if I run this, ta-da! Checker pattern! Woohoo! How cool is this, right? I could also use this for the rectangles and make it a bit more solid. Each one of the previous rectangles before. So the solid rectangle, the border, etc. So solid, border, and checker pattern. Whatever your taste is, okay? So this is pretty cool. I sometimes like keeping the pound sign. I like the hackery style of using actual characters instead of, but I think for the checker pattern, this one is cooler. So I'm going to leave the pound sign for the previous rectangles, and I'm going to leave this one for the checker pattern. All right, cool. Let's try another. Let's keep trying more stuff, right? The next drawing, the next wonderful ASCII object we're going to design here is going to be a pyramid, okay? And for the pyramid, things are going to be a little more nuanced. We're going to have to play a little bit more with the numbers. So that's why I want to first take some time and explaining diagrammatically what we're going to do. And actually, this is also an advice that I want to offer to any viewer that is checking this video and that wants to make art with computers. Do not underestimate the value of actually spending some time drawing and like breaking down the rules of what you're doing with paper and pencil, because it will actually make things much easier once you actually start designing the code. Okay, so what I'm going to do is I'm going to draw a pyramid. Okay, the pyramid is going to look something like this. And because the pyramid has a very clear rule that it has to have these two slopes at 45 degrees, in this case, I'm not going to be able to control both the height and the width. What I'm going to do is I'm going to take one of those defining parameters. So for example, it's going to be the height, and then based on whichever height for a pyramid I want, I will calculate the width that I need for that particular pyramid. Okay? If that's the case, then for example, for this example, what it follows is that if I have a pyramid of 5 pixels units height, and remember that we're using pixels and characters, in this case interchangeably, if I have a pyramid of 5 units high, because the pyramid has the top pixel at the center and it doesn't double, then it follows that the width of the pyramid is going to be 2 times the height, so it's going to be 10 minus 1 unit. Again, because this is at the center and the width of the pyramid is going to be even. All right, so we will know that the calculation is whatever the height of the pyramid 2 times minus 1. And it will also be useful to think of where things are in our pyramid. And remember that we were using this notation for the for loops where the coordinates of each pixel start from 0. Oh, and I made a mistake, sorry, here. I'm sorry, this is J. Where is my... This is J here. Oops. What am I doing right now? Okay, so this is J and this is I. Sorry. So I is where we are on the row and J is where we are so which, you see the diagram. Don't make me say this. It just makes it more confusing. So we have a system where each pixel, for example, this is pixel 2, 1, because we use I first. We use I first where we are on the horizontal row, and where we are, we use J, so where we are on the column. Okay? So let me just keep that there. Okay, so what we can see is that for us, a very important point will be the center of what this pyramid is, because that is what defines where we start checking for when we should be turning pixels on and off. And the way we're going to do this is we're going to check if we should be having a pixel on and off by saying we're going to count over I. All right, we're going to start moving to the right here in this direction, and then we're going to check the value of I. And if the value of I is equal to the value of the center, which we can calculate programmatically, it will be the value of the width, the value of 9 minus the value of the height, right? So it will be 9 minus height. If we move to the right and we say, if I is going to be equal to this value, then we will want to turn that pixel on. But if we only apply that rule, we will only be turning this pixel on, this pixel on, this pixel on. So we will basically create a column at the center of the pyramid. What we want to do is we want to also incorporate to the rule that we are moving down on the pyramid. So what we can say is, as we move to the right, if I is equal to this value minus where we are in the row, so minus 1 pixel, minus 2 pixels, minus 3 pixels, etc. If I is greater than this, if I is greater than 4 minus 3, in this case 1, if it's greater, and if it is smaller than 4 plus 3, in this case 7, if it is contained within this range, then we want to turn that on. And we're going to be using the value of I, so where we are. We're going to be comparing it to the center, and we're going to say if that is greater, if I is greater than this value minus where we are here, and if it's smaller than this value 4 plus where we are here, then that's what we will do for the rule. Was this clear? Talking about these things is sometimes so difficult, but I think you see the rule. So I'm going to relate I to the center of the pyramid, and I'm going to check that it is within the boundaries of I minus, so the center, minus the width of the pyramid at this point, which is coincidentally also the number of the row at which we are in the pyramid. All right? Sorry for that. Talking about these things is not easy sometimes. So we're going to see that the code for that is actually really clean and really straightforward. Let's take a look at how that will be implemented. All right, let's do this. So I have created two nested for loops with I and j starting at 0 and going up to some value that I haven't defined yet. And if we look at the diagram again, I would like to remind us that first of all, we're going to fix the height, then we're going to calculate programmatically the width that we need for that height, and then we're also going to calculate the value of the center so that it's easier for our calculations. So what we're going to do is, before we start, we know the height came from the user or the original parameter. What we're going to calculate now is going to be the pyramid width is going to be equal to 2 times the height minus 1. That was what we defined, what we saw here with the diagram. Whatever this is going to be 2 times minus 1 unit. And then the center row, the center column, sorry, is going to be equal to the height of the pyramid minus 1 units, right? The position at which that is equal to the height of the minus 1. All right. So now we can very easily just fill in here. So j, remember, goes from up and down. So that's going to be has to be less than the height, and I has to be less than the width. So if I is less than pyramid width. And now here, what I can check, I have to check whether if I is contained between the range of the center minus the row minus j and contained between the center plus j. So I can say here if I is greater than center column, if greater or equal than center column minus j, and I is less or equal than center column plus j, if that is the case, then write line a pound sign. Otherwise, just write line a dot. Is that, let's see if this works. I probably have messed something up. Let's take a look. I totally messed something up. Yes, I forgot I wrote here right line, so every character gets written to a new line as opposed to just writing them on the same line. So I'm just going to replace this, and let's see if that works. Oh my god, it works! First time! Woohoo! I love that. Woohoo! Obviously, we could also replace this pyramid, these characters with full blocks or not, but I do actually, for this one, I like keeping sorry, I would like to keep the I don't know what to say. I'm losing. I would like to keep the pound sign, and I would like to keep the dots because they actually look like the sky in some way, in some strange way. Something that we could extend. So we could extend this idea also to doing a full diamond. So we could also find some numerical rules to say what is the height, what is the center value, and then as we pass, then start working with the value of j in a different way after we have passed the center of the pyramid. Also, things that we could do is like we could find if we are exactly at the border of the pyramid and then draw like a forward slash like this. We could also find if we are exactly at this border of the pyramid and then draw a backwards slash. And we can do all those things together, including with a pyramid, with a diamond. But that, I'm going to leave that up to you, the viewer, to give it a try. And I'm going to do the last exercise, which is going to be trying to draw a circle, actually, within this ASCII art. Let me show you how that works. As I said, it's very useful very often to draw diagrams and to get a clear idea of how we can write algorithms to make these things. So I also drew the here like the shittiest, sorry, I should not say that word, a really bad really bad grid of pixels, right? And then what we want to do here is we want to say, imagine that we have a circle that is centered in this grid of pixels, all right? And the center is somewhere here and we have a particular radius, right? We want to make a rule where we say, well, I'm going to calculate the center. I'm going to look at the center of each one of these red pixels. And if the center is inside of this circle, then I'm going to turn it on. But if it's outside, I'm going to turn it off. But then how could I do that? How could I actually calculate that? Well, I know the coordinates of each one of these points because I know I have I and I have j, so I have like x and y for each one of my pixels. So a very simple rule that I can apply is I can do some trigonometry and say if I'm going to calculate this coordinate, I'm going to calculate the distance of this pixel to the center of the circle, and if that distance is less than the radius, then this pixel should be off. But if the distance is greater than the radius, then no, actually the other way around, sorry. If the distance is greater than the radius, then this pixel should be off. But if the distance is less than the radius, then this pixel should be on. All right, so for this one, it will be off. For this one, it's going to be on. And how can I calculate the distance? Well, I don't know if you remember, but the distance between 2 points, I have videos on my on my geometry gem. The distance between 2 points is a triangle like this. And I can do the Pythagorean theorem where I can say the distance between the 2 points is the square root of their x distance times their y distance square. All right, I have a video on that. That should be popping up somewhere, or it should be in the description. Or you go to the geometry gems, and then you can see this algorithm explained. It's just a Pythagorean theorem, very easy. So let's take a look at that. What we're going to do is we're going to write 2 nested for loops, and for each pixel, we're going to calculate the distance to the center, and then we're going to decide if we should turn on or off that pixel. All right. Let's take a look at how to write that code. Okay, so very simple. I have created here a circle, and sorry, I haven't created the circle yet. I have created 2 for loops, right? Where j is going to iterate between 0 and height, and I is going to iterate between 0 and width. Okay, because we might be in a rectangular situation. This is very common for example, for screens. And what we need to do now for each one of these pixels with their I and j coordinates, calculate the distance to the center. But what is the center? That is something that we can very easily calculate. I'm going to create a double, and I'm going to say center x is going to be equal to half the width, so width divided by 2, and then double center y is going to be equal to height divided by 2. And remember that for this one, I'm using doubles because the width and the height might be integer, but might be even, but might be odd numbers. So that's why I want to divide this. And to avoid integer division, I'm going to make sure to cast these things to doubles. Okay? Oh, alternatively, no, actually, something that I could do to make sure that this works is I could divide by 2.0, and this is also an implicit way because this is forced to be a double. This will be a real division. So now that we're here, for each one of the pixels, I can calculate the distance to the center. So I can say, for example, I'm going to create a variable called d, and this is going to be equal to math the square root of the 2 distances added together. But I don't have the distances yet. So let me calculate this. So double dx is going to be equal to whatever I is minus the coordinate of the center. Okay? And the sign doesn't really matter because I'm going to multiply this. I'm going to square this. So this is going to be dx times dx. And then double dy is going to be equal to where we are in j minus center I. And then this I'm going to add here dy times dy. So here I've calculated the distance from where I am in the horizontal to the center, the distance, vertical distance of where I am in the rows to the vertical center. I have calculated the distance by doing the square root of the squares of those 2 values, all right? And now with that distance, I need to decide whether if I turn this pixel on or off. So what I need to do is if d is smaller than the radius, but wait, what is the radius in this case? All right, where am I taking it from? Well, I could either say, let me write a value here that is going to be double the radius, and I can either hard code this to a number, or I can say whatever the value, whichever value is smaller, the width and the height, I'm going to use that as the value. So, I'm going to use the value of half of that. So what I can do is I can say if height is smaller than the width, then radius should be 0.5 times the height. All right? Otherwise, if that's not true, oops, sorry, then radius should be equal to 0.5 times the width. What I'm saying here is because I can have two situations where my screen is like this, my rectangle is like this, or my rectangle is like this. I want to find which one is the smaller dimension and then fit the radius to half of that, or whether if the width is the smaller dimension and then fit the width to fit the radius to half of that. All right. Now, with this value, if d is smaller than the radius, then print to the console, console right line, not just right, the pound sign. Otherwise, console right, just a simple dot. Let's see if this works. I'm going to run this. Come on, come on, come on, come on. Woohoo! It actually does work. Let me crank up the value of let me make the height, for example, also 40. This is going to give me, instead of squares, it's going to give me rectangles that are, but you can see now how we're getting a circle that is actually, because the pixels are basically rectangles, they're not perfectly square, that's why everything is like squished out and it looks more like an ellipse rather than a circle. But you can see that it's doing like a nice smooth transition here. Also, if the height was 80 instead of 40, you would see how the circle actually adapts to that center because of the rules we just explained. You see how the circle is actually nicely being centered in the vertical, or if this was much wider than this one, for example, the rectangle is also going to fit, and the circle is going to fit exactly at the center and nicely within the rectangle here. Woohoo! All right, the last thing that we're going to do is we're going to accept some user input for the width and the height, so that it's a bit more interactive. I've done this in previous videos, taking user input and then converting it to the right type. So for example, here we can say console right line. So for example, right type a rectangle width. And actually, sorry, I actually need right line. So right, and then here I need width string is going to be equal to the input that I'm going to get from the user. So console read line. All right, and then I'm going to type another. Okay, so now I'm going to say I'm going to type in a new empty line so that I don't write right on top. I'm going to copy and paste this, write the rectangle height, and then this is going to be height of the string, and then this, after getting those, I'm going to try to cast them. So I'm going to do convert to int34, and this is going to be height string, and convert to int34. This is going to be width string, and I'm actually writing then the opposite. Sorry, so this should be height and this should be width. Okay, and with that, I think I could actually. All right, so type a rectangle width. So that's going to be 50. Type a rectangle height. That's going to be what? It's going to be 25. And then boom, I get the results with that geometry. Okay. And you have seen in my previous videos also how to make sure that the input that was input here is numerical and there is not an error in the conversion. Okay, so how to check that this is not any string or like some gibberish but an actual number. I think that was back in my exercise video for the calculator, the interactive calculator, which is back in this playlist at some point before. Okay. All right. So let me print this again, like the Triumph 60 and 40, and boom. Alrighty. Okay. Yoo-hoo. ASCII art. So I hope this was interesting to understand, first of all, how to do repetition and how to work with nested for loops. That's one thing. Second thing, how to look at the numerical rules of where each one of these characters is in a row and in a column, and how to use that as a way of turning these pixels on and off. And third, everything that we have just seen here is the core of how computer graphics work. We have been working with characters on a console application, but if instead of characters this was actual pixels, this would be for us a way of turning tiny pixels on a screen. It's just that the dimensions will be much larger. We will also have color as an option, but at the end of the day, the foundations of how to actually draw a circle on a computer screen with actual pixels is exactly the code and is exactly the logics that we have broken down in this exercise. Okay, if you were writing code for Photoshop or Illustrator and you wanted to represent those circles or those geometries on the computer screen, the code that you will be writing would be very similar in spirit and in logic to what we have seen today. But instead of characters on a console application, it will be actual pixels from your screen, which I think it's amazing, and I think it's a really good foundation to start understanding computer graphics, for example. So thank you very much for holding on. If you like what you saw here, please feel free to subscribe, to turn on the notification button, to stay up to date to all the videos that we post. And if you were watching this as part of the Learning C# series, I'll see you in the next video. I don't know what we're talking about next, but I think it's probably going to be interesting and you're going to like it. Thank you. See you in the next video.